Hi everyone. So today we're going to continue on 9.2 conservative vector field. So last video we get to talk about try to answer the two questions that we want to figure it out. The first one is, how do we identify if a vector field is conservative or not? And we discovered that a conservative vector field, every time when we evaluate a closed curve integral, we always end up having zero, and therefore become something that we can use to identify them. And according to that, along with Green theorems, allow us to define something called the conservative consistency condition, which is right here. That basically say that df2 over dx must equal to df1 over dy in order for a vector field to be conservative. So we've gone for two examples. So what I want to do today is to go ahead and try to figure out, now that we know how to identify a conservative vector field, is there some way to now try to come up with the potential function? So the next question is, let's say given a conservative vector field f, how to find its potential function. So that's the big question. So I guess the easiest way to do is go ahead and try an example. So here is my first example. Let's say we're going to let vector f of xy to be equal to 2xy squared minus 3y, 2x squared y minus 3x plus 8y. So the first thing I would like you to do is the following. Is f conservative? Now, of course, you should expect that it is conservative, but let's try to find out. So in this case, what I'm going to do is I'm going to do df2 over dx, which is d over dx of 2x squared y minus 3x plus 8y, which come out to be 4xy minus 3. And we're going to do df1 over dy, which is d over dy of 2xy squared minus 3y, and that come out to be 4xy minus 3 also. So notice that these two things tell me that df2 over dx is equal to 4xy minus 3, which is equal to df1 over dy. So therefore, the consistency condition has been met, and we know that f is conservative. Now, if it is conservative, now we must be able, that means the potential function must exist, and now it's just a matter of trying to find the potential function. So this is something new. Now, how do we find the potential function of vector f? So the idea here is to understand that if vector f is indeed the potential of the gradient of a potential function lowercase f, then therefore would imply that the gradient of this conservative view vector f must be the partial derivative of lowercase f. So let's try to use that to our advantage. Let's say we're going to let f of x, f of vector x, or f of xy, be the potential function of vector f. So therefore imply that vector f must equal to the gradient of lowercase f. So if that's the case, then that implies that 2xy squared minus 3y, 2x squared y minus 3x plus 8y must equal to df over dx, df over dy, because that's the gradient of f. Therefore, result in the following. Result in that we know that df over dx must equal to 2xy squared minus 3y, df over dy must equal to 2x squared y minus 3x plus 8y. So now we know these two partial derivatives must be true. Now all I have to do is try to figure out how to find f that would satisfy both of these partial derivatives. So there are basically two ways to do it. You could either start with df over dx or start with df over dy. It's really up to you which one you want to go, because you will have to use both of them to try to put together to find f. It's just a matter of which one you start first. So I personally always like to start with df over dx, and I always do it that way, because regardless which way you do it, you get the same answer. So I would rather be very consistent so that I know what I have to do every time I see a problem like this, because I do it the same way every time. So that's what I'm going to show you, but feel free to try using df over dy. The process to find the potential function is symmetrical. So if you start with df over dy, it works out exactly the same thing. You just basically flip-flop the two, some of the procedure. That's all that is. So we're going to start with df over dx, which is equal to 2xy squared minus 3y. What I'm going to do is kind of just move the dx over, and then I'm going to integrate them. And so when I integrate df, I just get f of xy. And then when I integrate 2xy squared minus 3y with respect to x, I get x squared y squared minus 3xy. Now here comes the important part. Normally we'll have a plus c, and it makes sense because a constant disappears in a differentiation and becomes 0. So therefore it makes sense to kind of reconstruct that missing constant by saying a plus c. The problem is that that was when you're doing a single differentiation. But what we're doing here is a partial differentiation. And because of that, not only constant are considered to be constant, but when I differentiate with respect to x, any function that only have y in it also considered to be constant. So therefore, in this scenario right here, what I'm adding is not a constant, but what considered to be constant when I differentiate with respect to x. And that would be some function of y. So g is a function purely of y that has no x in it, because if there's an x, it will change the partial derivative df over dx. So the fact that it disappears when I differentiate with respect to x tell me that it's a function of y only. And if you do a quick check, if you take the derivative of this thing right here with respect to x, you find out that g of y would go away because it's a constant with respect to x. And therefore you have 2xy squared minus 3y. Now come the next part. The next part is to try to figure out what g of y is. So to do that, we're going to try to make use of f of df over dy. So to do that, this is what we're going to do. Instead of go ahead and integrate again, what I'm going to do instead is to take the derivative of this function. And when I do that, I get 2x squared y minus 3x plus g prime of y. And why we know that that is what f2 is, so therefore that should equal to 2x squared y minus 3x plus 8y. Notice that these two things kind of matches up. Oops. And therefore implied that our g prime of y should be what 8y is. And if that is the case, now I have a way to figure out what g prime of y is. So if g prime of y is equal to 8y, then therefore imply that g of y should be equal to the integral of 8y dy. And that come out to be 4y squared. Now remember, when we integrate, we have to put in a constant of integration. In this scenario right here, since we already know that g of y cannot have x in it, but it can still have something that considerably constant when I differentiate with respect to y, and that is just regular constant. So I'm going to call that c. And that gives me what g of y is. So now if I put everything together, now I can form my function. F of xy should equal to x squared y squared minus 3xy plus g of y, which we find out to be 4y squared plus c. This is our potential function. And it shouldn't be too hard for you to just take the derivative of this thing with respect to x as well as with respect to y to see that you have the vector f. So if I take this df over dx, then I'm taking a derivative with respect to x of x squared y squared minus 3xy plus 4y squared plus c. That come out to be 2xy squared minus 3y, which is exactly what we have as f1 right there. And if I take the derivative of f with respect to y, I would see that this is just taking the derivative of that with respect to y. So that just becomes 2x squared y minus 3x plus 8y, which matches f2 right there. So this come out to be f1, this come out to be f2, which show that we have a correct answer. All right, I guess we have time for one more example, and that would probably be it. So let's try this one. I'm going to go and let f of xy equal to 2xy plus 4x squared plus cosine 2y, and then x squared minus 2x sine 2y plus 1. So first I'm going to ask you to show that f is conservative. And once again, remember, you should know that it is conservative, okay, because it's an example that try to illustrate the conservative property of a vector field. But let's go and do this. So I know that f1 is basically this right here, the first thing, and f2 is the second one. So I'm going to do df2 over dx, which is d over dx of x squared minus 2x sine 2y plus 1. So derivative of x squared would be 2x minus derivative of 2x sine 2y. 2 sine 2y considered constant. The derivative of x is 1, so therefore just become minus 2 sine 2y. And derivative of 1 is 0, so that go away. Alright, let's hope the other one come out to be the same thing. Hopefully I didn't make a mistake when I write the problem. So df1 over dy would be d over dy of 2xy plus 4x squared plus cosine 2y. So 2xy, when I take the derivative with respect to y, is 2x. Derivative of 4x squared actually go away because that doesn't involve y. And the derivative of cosine 2y, according to chain rule, is negative 2 sine 2y. So therefore, we do have the consistency condition. So it checked. F is conservative. So now it's just a matter of go through the same exact process to try to find the potential function. So once again, we're going to let f be the potential function. Of vector f. So therefore imply that df over dx is equal to f1, which is equal to x, oops, sorry, wrong one, is 2xy plus 4x squared plus cosine 2y. And df over dy would equal to f2, which is equal to x squared minus 2x sine 2y plus 1. So once again, it doesn't matter which one you start. You're going to have to use both anyway. So I'm going to just start with df over dx once again. Because once again, that's how I like to do it. So df over dx is equal to 2xy plus 4x squared plus cosine 2y. So I'm going to go and move the, actually I'm going to just do that right now. I'm going to say just, that means df would equal to this dx. And I'm going to integrate both sides to see what happens. So if I do that, on the right side, on the left side I have f of xy. On the right side, I have to integrate everything with respect to x. So 2xy would become x squared y. 4x squared become 4/3 x to the third. Cosine 2y is a constant when I integrate with respect to x, so therefore become plus x cosine 2y. And of course, don't forget, plus some function, plus some function of y that we don't know. But it is considered to be constant throughout a differentiation with respect to x. So now what I'm going to do is try to take the derivative of this tentative function f with respect to y and see how it compares to df over dy or f2. So if I take the derivative of this thing, I will have df over dy, which would equal to x squared. 4/3 x to the third would completely go away. Derivative of x cosine 2y, x is a constant, cosine 2y, the derivative is negative 2 sine 2y, so become negative 2x sine 2y plus g prime of y. And that has to equal to x squared minus 2x sine 2y plus 1. So notice that we have the x squared and the x squared and the minus 2x sine 2y minus 2x sine 2y. And therefore leave me with just g prime of y equal to 1. If you do the problem correctly, you should always be able to get rid of everything except g prime of y, which then allow you to identify what g prime of y should equal to. So indicate g prime of y equal to 1, so that's pretty simple. That means g of y must equal to y plus some constant c. And so now I have my answers. Our function f of xy must equal to x squared y plus 4/3 x to the third plus x cosine 2y plus y plus c. And it shouldn't be too hard to do a quick check. If I take the derivative with respect to x, I get 2xy plus 4x squared plus cosine 2y, which, if I'm not mistaken, that's exactly what f1 is. So that checked out. If I take our answer f and take the derivative with respect to y, I get x squared minus 2x sine 2y plus 1, which is exactly what f2 is. So that check out also, and therefore show that our answer should be correct. I believe it or not, that's actually the end of 9.2. There's really not that much things I want to show. Actually, you know what? Since we have a little bit of time, maybe I'll show you one more example. Since we have time, I'm going to show you one more example. Now, the consistency condition that we define here allow us to define if a function is in R2. So what if we have a function that's in R3? Can we still also find out whether it's conservative or not? Well, yes, we can. We just have to modify our condition a little bit more. So let's say for a vector field that map from R3 to R3. We know that f is conservative if this is true. If the curl of f is equal to the 0 vector. And notice that that makes sense because the condition, the consistency condition for R2, for function map from R2 to R2 is basically the scalar curl equal to 0. So now you have a function map from R3 to R3, that makes sense that now we have to take the entire curl and set it equal to 0 to show. So based on what you remember, curl from 8.4, curl is df3 over dy minus df2 over dz, df1 over dz minus df3 over dx, df2 over dx minus df1 over dy, and we need that to equal to 0, 0, 0. And therefore result in the following consistency conditions. That will be df3 over dy minus df2 over dz equal to 0, imply that df3 over dy equal to df2 over dz. And df1 over dz minus df3 over dx should equal to 0, imply that df1 over dz must equal to df3 over dx. And then finally, that is the consistency condition for function that map from R2 to R2. That's df2 over dx equal to df1 over dy. So these three conditions must be satisfied in order for us to know that a function is conservative. So now I'll show you a very simple example to illustrate this process. Let's say we're given vector f of x, y, z is equal to y, z plus z, xz, xy plus x. We're going to show that f is conservative, and we're going to try to solve for its potential. Potential function, I guess. So let's see if we can show that it's conservative. So I'm going to go and show basically these three conditions right here. So df3 over dy, which if I look at df3 over dy, that would be derivative of xy plus x, which is just x. And is that the same as df2 over dz? And yes, it is. Because xz, the derivative of that with respect to z, is just x. Now, next one is df1 over dz, which if I take df1 over dz, I get y plus 1. Is that the same thing as df3 over dx? Which it is. It's y plus 1. df2 over dy would actually be 0 in df2 over dx. That would give me z. And that is the same thing as df1 over dy, which is also z. So therefore, the conservative condition is, the consistency condition is satisfied. Vector f is conservative. So now comes the big question. How do I figure out what is the potential function? So let's go and do the same thing. I'm going to go and let f of x, y, z be the potential functions of f. So therefore, imply that df over dx should equal to f1, which is yz plus z. And df over dy should equal to f2, which is equal to xz. And df over dz should equal to f3, which is xy plus x. So how do we actually deal with this three different partial derivative? Well, we'll do it the same way as before. So what I'm going to do is I'm going to start with df over dx again, and I'm going to say df would equal to yz plus z dx. And so if I integrate both sides, I get f of x, y, z must equal to x, y, z plus xz plus constant in the differential with respect to x. And I know that a constant obviously considered to be constant, but any function that only involve y and z are considered to be constant when I differentiate with respect to x. If I have any x in it, it will change our partial derivative with respect to x. So therefore, I'm going to call this g1 of yz. And yes, I know the subscript kind of give it away because we will probably have some kind of g2 later on. So now the next thing I'm going to do is this. I'm going to go and take this thing. I'm going to differentiate this with respect to y and see what happens. So if I do that, I get xz plus dg1 over dy of yz. Yes, you do have to identify that that is only differential with respect to y. And that is df over dy. That should equal to f2, which is xz. Fortunately for us, that tells me that dg1 over dy must equal to 0. And so that would tell me that this g1 is a constant? No. Remember, this is a partial derivative with respect to y. And therefore, anything that's not function of y considered to be constant. And what's considered what's not a function of y? A function that only involves z. So therefore, this implies that g1 of yz must just equal to some constant function of z only. So therefore imply that our function f of xyz must equal to xyz plus xz plus some function that only involves z. If it involves y, it will change our df over dy. But in this case, it doesn't. So now what I'm going to do is repeat the process. I'm going to take df over dz, which if I do that, I get xy plus x plus g sub 2 prime of z, and I'm not going to use the d over dz because there's only one variable now, so I can just use prime without worry about it's not clear as to what derivative are we talking about. And that should equal to f3, which is xy plus x. So therefore, this implies that g sub 2 prime of z is just equal to 0 also. And therefore tell me that g sub 2 of z is just equal to some constant. That does not involve z, because otherwise the derivative won't be 0. And so, I can finally put my answer together. That just equal to xyz plus xz plus some constant c. So if you look, if you take the derivatives with respect to x, y, and z, you should realize that if I do this, if I take df over dx, I get yz plus z, which happen to be f1. If I take the derivative of that with respect to y, I get xz, which is happen to be f2. If I take the derivative of this thing with respect to z, I get xy plus x, which is happen to be f3. So they all checked out. So that convinced me that I think we have the right answers. All right, And that would actually be the end of 9.2. So we talk about how to identify conservative field and also how to find the potential function. Now I know that our last example is in R3, but for your test, in-class test at least, we're only going to be doing in R2. Take-home tests on the other hand could be different. Okay? All right, that's it for this video, and I'll talk to you guys again soon. Okay? Bye-bye.